All right, chapter 5 is about probability and simulation. Um, some students and I guess some teachers and think that probability is one of the more difficult sections in the textbook, and I can say that over the years my probability scores on the AP Stat test have kind of been the lowest sub scores, I guess. So I don't know what that really means. Just stay on top of it and try to do a lot of practice problems, and it will come better. Um, So first of all, we're going to talk about simulations. Why do we need simulations? We're going to kind of circle back on that here in a bit. Um, this is a couple. We did a couple activities in class the first day. So if you missed these activities, I'm not gonna do them here, but I'll just talk about them. The Monte Hall problem is a pretty popular problem. I think about half the students in the class had heard of the problem before. It comes from the TV game show Let's Make a Deal, hosted by Monty Python. Basically, to make a long story short, and like I said, this is about a 30-minute activity in class. Um, at the end of the game show, whoever was the winner of the game show, the final event was Monty Hall, the host of the show, would present three doors for the contestant. Behind one door is a car, and behind two doors are goats. So the contestant had to try to pick the door to win the car. So, but there was a little twist on it. So the first thing the person would do is they would pick a door. So I'm going to pick door number one. So what Monty Hall would do after you pick door number one, whether you got the car or the goat, one of the other two doors would have the goat. And he knew what was behind the doors, so he would open up one of the doors that has a goat. And then he'd give you a choice. He'd say, you can either stay with door number one, or if you want to switch, you can switch. I'm going to stay with door number one. So I got a goat. If I would have switched, I would have won. However, if the car would have been on door one, then if I would have switched, I would have lost. So this game show went on for, I guess, several years. I don't really know. Um, but what happened was there was a columnist for Parade magazine. Her name was Mary. I don't know how to pronounce it exactly. Mary Vos Savant. Anyway, she was in the Guinness Book of World Record for the highest IQ at the time. There was one test that I guess she got like a 228 or something crazy. So she was kind of generally accepted to be the highest IQ person, if you want to call her the smartest person around. And they wrote a call. Somebody wrote in and asked, um, "Is it to your advantage to switch the doors, or should you stay, or does it even matter?" So it's a probability question. What's the probability that you win if you keep the door, and what's the probability you win if you switch the doors? So in class, I asked you guys to ask the class to calculate what do you think the probability is that you would win if you stay. And I think most kids would probably say, well, if you pick, there's three doors and one of them's got the car. If you pick, what's the probability you pick the right door and you stay with the right door? That's a 1 out of 3. That's a pretty easy one. And then what's the probability you win if you switch doors? So that's kind of the one that was a little bit tricky. A lot of people guessed 1/3. Some people guessed 1/2. Other people maybe guessed 2/3, or who knows what else, what other guesses there could be. Mary Savant, or in the column, wrote that she said that if you stay on the door, you got a 1/3 chance of winning. However, if you switch doors, you have a 2/3 chance of winning. Well, this caused a bit of an uproar at the time. This information from this Wikipedia page, anyway, says that 10,000 readers wrote into the magazine. Most of them claiming that she was wrong. In fact, nearly 1,000 PhD professors wrote in, many of them claiming that she was wrong. I don't know if all of them did. I'm sure all of them did not. So there was, it's a bit of a stir. You got PhD statisticians saying that she's wrong, and as it turns out, she was actually right. If you switch doors, it does double your chances of winning, and this was verified on the game show, and then also through simulation. So why do we need simulation? Well, simulation helps us calculate and estimate probabilities when either theoretical models are too complex to calculate or um, are difficult. In this case, this is a case where intuition, at least for these, PhD guys that were writing in telling her that she was wrong, their intuition was not holding up. Or I don't know, maybe they tried to theoretically calculate it. I don't know. Um, Regardless, what we did in class was I didn't actually give out the answers right away. We actually did a simulation and had people choose cards and simulate to see what your winning percentage is here and here. This website, if you play a few times, I think I said play again. I picked door one. I'm going to switch this time. There, I won the car. But that's two trials. That doesn't really mean a whole lot. That I won one and I lost the other. But this data right here kind of tells us the percentage of the time. If you switch, apparently people have played this game 420 times today. If you switch, people have won about 66% of the time. And if you don't switch, people have won about 36% of the time. And that's out of 372 trials. So that kind of tells you that looks like, I think I stayed and I lost that one. Looks like you double your chances if you switch. So this kind of verifies it. I thought, like I said, I don't know off the Wikipedia page. I also read this here that this guy here, I don't even know how to pronounce his name, but he is considered one of the most prolific mathematicians in history. He remained unconvinced that Mary Savant was right until a computer simulation demonstrated it in 1999. That was, like 9 years after. Anyway, the point is, probability isn't so clear. Why is probability difficult? Because sometimes our intuition can be counter to the actual probabilities. Sometimes we're going to use our intuition to calculate probabilities. Other times we're going to use theoretical models. Sometimes the theoretical models are going to be really difficult and we're going to want to use our intuition. Sometimes our intuition will fail us and we have to, that's just why it gets a little bit difficult. We're not going to get into any crazy probability in this class. This isn't a class on probability. This is a class on statistics. However, we need to talk a little bit about some basic probability so that we can do our statistics down the road. All right, 5.1. Let's just go through this. We'll see how far we can get in the next 6 or 7 minutes. An important fact emerges when we observe a random phenomenon or random sampling. We're going to kind of focus on random phenomenon, but later on we'll talk about sampling. Chance behavior is unpredictable in the short run, but has a regular predictable pattern in the long run. So random chance behavior is unpredictable in the short run, but has a very predictable pattern in the long run. When I played this game, if I play it one time, there's no telling whether I win or lose. I picked Dorn 1. Okay, I lost. But that doesn't really mean anything. It doesn't mean that every time I stay at the same door, I'm going to lose, and every time I switch, I'm going to win. On the short run, anything can happen. I could win 3 times by staying on the door, and I could lose 3 times by switching in the short run. And that wouldn't be all that unusual. But if you do it many, many times, if you do it 420 times or 400 times, then the true probabilities start to come out. We can actually we can predict what happens in the long run. The law of large numbers, put a little star by it. This is kind of the foundation of probability for AP statistics. Law of large numbers says if we observe more and more repetitions of a chance process, the probability of times that specific outcome occurs approaches a single value. That value is called the probability of that outcome. You can kind of think of it as a limit if you've studied a little bit of calculus. The limit as the number of trials approaches infinity. In fact, it even looks kind of like a limit. In the short run, things are going to kind of hop all over the place, how frequently something occurs. But over time, it's going to kind of hone in on a single value. And that single value is defined to be the probability of that event. So the definition of probability isn't a kind of a theoretical definition. It's more a long run occurrence type of definition. The probability of any outcome of a chance process is the number between 0 and 1 that describes the proportion of times the outcome would occur in a very long series of repetitions. So let's kind of explore this a little bit. I have a little probability applet from our textbook. So I have the probability set to 50%, kind of like a coin toss, I guess. And if I toss it one time, so I got a heads. I think I'm recording the proportion of heads. So that's 0%. So I'm way down here at the bottom. Toss it again. Okay, I got a tail. So I'm at 50%, maybe what you'd expect. So there I got 3 or 4 heads in a row. Then I'm getting 4 tails in a row, 5. So as you can see, the probability in the short run is very unpredictable. Like I have no idea what the next one's going to be. It doesn't matter if I got a couple heads or tails before. The next one is really going to be kind of unknown. So in the short term, really anything can happen. It's unpredictable. However, if I toss this thing 200 times, let's toss it another 200 times. So this pattern that was, or lack of a pattern that was going up and down and very unpredictable in the short term, kind of tends to balance out and be pretty predictable in the long run. So if I show the true probability there, now this is a little bit interesting. For some reason, I tended to get a few more heads early on, and it kind of put me significantly above 50% a little bit. And the model really hasn't quite been able to catch back up and get down to that 50%. So you might say, well, geez, that's not 50%, but 200 isn't really enough either. If you flip it 300 times. Oh, actually, I'm at 600. My bad. I thought I was doing 100 at a time. So this is having a little bit of a hard time getting. In fact, I just moved a little bit further away. But that happens. We haven't done enough trials yet. If you were to do 1,000, 10,000, 1,000,000 trials, it should approach that 50%. That's interesting that it's off by a little bit. We should try another one. Toss. So this one just happened to stay a little bit closer to the 50%, maybe even dipping a little bit lower. That's kind of usually what you see. It usually kind of hangs around there, might go up a little above and a little below. But on occasion, every once in a while, if it gets a little bit off, it takes a little bit of time. A little bit of time, as in a couple thousand trials, perhaps, for it to get, closer to the true proportion. So there isn't a certain number of times that you have to flip it. Sometimes you can get pretty close after 100 or 200 trials. Sometimes it might take 10,000. So unpredictable in the short run, but predictable in the long run. That's the law of large numbers. Myths about randomness. The law of large numbers tells us that randomness is predictable in the long run. However, randomness is not predictable in the short run, although our intuition often tells us that it is. So this is another little activity we did in class. I'm not even going to really, well, I guess I could just talk about it. I guess I got another minute or so. Basically, we had kids generate their own sequence of heads and tails. So like, imagine in your mind you're flipping a coin. I get a heads, I get a tails, I get a heads and a heads and a tails and a heads. And I had the kids do 50 of those just from their own, what they think happens. And then I had them actually flip a coin and record the heads and tails. And what we found was there was a pretty distinct pattern between the longest run in these and the longest run of those. Like this would be a run of 2, this would be a run of 4. Whenever humans generate sequences of heads and tails, you tend to just get maybe runs of 2, 3, or maybe even 4, maybe 5. But when you do a random process, sometimes you'll get 8 in a row or even 9 in a row. So there's a pretty significant difference in human-generated outcomes versus actual randomness. Moral of the story, main idea, humans cannot generate random numbers, as we learned in sampling. And then the secondary idea, randomness is not predictable in the short run. It has no memory, even though you do, the coin does not.